Okay, so let's go ahead and look at this one now. And what we're doing is we're going to match the function. This is the function, and these are the derivatives. Okay, so one of the things you're trying to learn right now is to be able to conceptualize what a graph of a derivative is. A derivative is a function, and it can be graphed. So if you look just kind of starting with, this is function A, right there. Okay, what we need to do is, when we do the derivative of that, the derivative f prime with that, we just need to figure out what the slope of the tangent line is. Okay, so look at this line and let's figure out what the slope is. Well, if you find like 2 points on the line, there's a good point there. That looks like a point 1, 1. So what's the slope if you just do rise over run? Looks like it's up 1, right 1. Okay, so that would be with a rise over 1. Okay, actually the derivative is the function f prime of x equals 1. So how do you graph y equals 1? That's a horizontal line, right? Okay, so that means that's going to match with that derivative right there. So what we have is for function A, that matches with, it looks like, capital C. Does that make sense? You find the remember, a derivative is the slope of a tangent line, and if it's already a line, then the derivative is a line, right? Okay, it will give that tangent line's a line, so you're doing the slope. Okay, now let's look, say, at B. So let's look at B. So if we're looking at, we'll call this like g of x. Okay, this is for B. All right, what's its slope? Is its slope any different? That looks the same. Okay, there's 2 points on that red line, so it looks like you're going up 1, right 1. So that means that when you do the derivative g prime, you're going to get 1 over 1. So that also is going to match C, isn't it? It's the same thing. Okay, it's the same derivative. So that means that this function B also matches C. Okay, you get the gist of what I'm doing? Okay. All right, okay, let's take a look at, let's go down to, say, D now, or let's do C. All right, so if you look at C, for function C, we'll call that h of x. Okay, this will be the function h of x right here. Okay, what's its slope? You can do that pretty much in your head. What do you think? I'm looking at C. Okay, I'm sorry, I'm looking at the wrong thing here. That's h of x right there. Okay, so what did we say? -1. Good, -1. So if you do that, it looks like you're going down 1, right 1. So you'd have a rise of -1, a run of 1. So that means that you would have a -1 slope. Okay, so what does that match? That's A. Good. Okay, so that means that this function C is going to match the graph of A, because that's the line -1. That's really y equals -1. This one right here is really y equals 1. So that's how that goes. Guys, that making sense? Okay, all right. Okay, well, let's see. The next one would be, I guess the only other one we need to look at then is D. So if you look at your function D, okay, I'll call that z of x, okay, or whatever. Okay, so that will be my z of x now. All right, what's its slope? Up 1, right 2. Okay, so that looks good. So that one looks like you would be going up 1, right 2. Okay, so that means you have a slope of 1/2. Okay, so that means that this one matches B, because that line right there is y equals 1/2, like that. Okay, so that's the idea. So it's actually easy if you have a line. If your function's a line, it's easy to tell what the derivative is, because it's the slope of that line. So it's going to be a constant function. Does that make sense? Okay, so that would be the idea. Now these things get a little bit more complicated, but we're going to work on this a little bit today, different types of functions and looking at their derivative. Okay, all right. So I want to go back. I wanted to do this one thing. I think I had a link on here that I showed you guys last time. I want to do this thing one more time. This thing is GeoGebra. I need to put this on D2L. This is actually a good thing to mess around a little bit with. So I'm going to just show you one more time on this. I'll take some sort of a function. Let's take like this function right here. Now this one in black is the function. what our goal is to graph the derivative. So this thing right here, that thing in blue, you can manipulate. The way you do a derivative is kind of like this. This is the way I'd start this off. So if you look at this point right here, what kind of tangent line do you have right here? 0. Okay, so that means the derivative would take on the value of 0. Okay, another place where the derivative is 0 is right there. Okay, right at the top. So that means you would go there like that. Okay, you would have to have that right on 0 like that. Another place the derivative is 0 is here, right around 4. So I'm going to do that. So that's how I would start the problem, is kind of by computing that. Okay? Now what you want to do is you want to think about what the derivative's doing. Okay? We know that the derivative is 0 there. But what kind of tangent line do you have right now? What kind of slope? Negative. So that means you're going to have negative function values on your derivative. If you look at that, that looks like a 45-degree angle, kind of. And if you have a 45-degree angle, the slope is either 1 or -1. In this case, it's -1. So I would probably conclude at -6, that would be around -1. And what's happening is it's still negative until it gets to 0. So the graph of the derivative is going to do something like that. Does that make any sense? Okay, remember, when you graph a derivative, you're graphing the values of the derivative on that function. So what I would do is just kind of slide this up here, and then just sort of slide that in somewhere like that, okay? Now, what will happen from here, if you begin to look at this, is from this point to this point, think about what's going on. You have a 0 derivative, but now what kind of slopes do you have? And they're getting bigger, aren't they? Okay, my pen is getting steeper. When I get there, it's probably about 45 degrees, so the slope's about 1. Then what happens is the slope starts getting smaller. It's still positive, it's going to get smaller. So this derivative from here to here is going to kind of do something like that. It's going to be positive values going up to 1 and then back down to 0 like that. Okay, does that make any sense? So you got to think about what the value of the slope of the tangent line is when you do that. So I'm going to conclude that around here, that has a value of about 1. I'm going to just kind of estimate that in, something like that. Now what you have is you have negative derivatives, right? And right around here, does it look like maybe the tangent line's 45 around there? Okay, so what's the slope?
1.
About -1, okay? Like that, then I can kind of do that. Kind of comes in like that, and then once I get here, the slope is positive again, right? From there on out, it's positive, about 45 degrees there, so that's probably about a slope of about 1 like that. So that's what I'm going to conclude that the derivative basically looks like. Does that make sense? Now, here's what's cool about this. I can check the accuracy. Look at that, the teacher got a 93%, okay? All right, then it shows the results. So it's real hard to get this perfectly good, but, you know, your goal on that is to get, you know, pretty accurate, 90%, something like that, okay? That's the idea. I've never got 100 on this. I keep trying, though, because I'm bored. I need something to do. So over the weekend, if you need something to do, try this. It's kind of a neat way to learn how to do derivatives. Okay, so back to where we were here. Okay, we're going to work a little bit more on that with this, and then we'll finish this up and start talking about continuity a little bit. So what I want to do with this is these are functions that are a little bit more complicated. So I'm going to look at just matching the function, which is the one in black, with the graph of the derivative, which is negative. Now, one thing that will help you considerably as you start learning derivatives, this one right here kind of looks like a cubic from college algebra. You know what I mean? Kind of like x to the third. One thing that happens when you do a derivative of x to the third, and we're going to work on these derivative rules today, you get a quadratic. So the graph of the derivative I know is going to be quadratic. So it's going to be a parabola. I know that. Now what I do on this problem is kind of this. This is what the key is. Right here, the derivative, I'm going to say f prime. I know f prime of x is 0 right there. Okay? So that would match like that. See that graph, that function value right there on the derivative is 0. What kind of derivatives do you have right in this part of the curve? Positive or negative? Positive. That's all that matters. And what's happening is that's a big positive number right there because it's very steep. So if you look at this graph, this matches the same thing. That's a positive value. Those are all positive values on the derivative, so it matches perfectly. Now, what is the derivative doing when you're to the right of this point? Still positive, isn't it? But it's small and gets steeper, right? So that means that you have positive values that are kind of small, but they get bigger and bigger and bigger forever. So that means that A is going to match the graph of D, like that, okay? So this thing right here is going to match that. Does that make sense? Okay? Logically, okay, remember, you are looking at the value of the slope of a tangent line, and you're plotting that in your derivative. Your derivative is a function that can be graphed, okay? Let's look at B, okay? Here's the way I'd look at this. Can you tell me on graph B how many places where the value of the derivative would be 0? That's a key. 3, good, okay? That would be places like that. See, the tangent line has a slope of 0 there, has a slope of 0 there, and it has a slope of 0 there. Just by figuring that out, there's only one possibility that would match. What would that have to be? C. Yeah, it'd have to be, because at -1, the value of the derivative is 0. At 0, the value of the derivative is 0. And at 1, the value of the derivative is 0. That's the only possibility. And what's happening on this problem is, if you look at this right here, this is a negative derivative right there. Look at this. Negative values for the function. Here you have positive sloping tangent lines, right? What do you have here? Positives right there. Okay? Then what do you have here? Positive sloping tangent lines. That's what you have here. Positive and so forth like that. And then finally it starts becoming negative again like that. Okay, does that make sense to everybody? Okay, remember, you're looking at tangent lines and what their values are. If they're positive, negative, or 0, that's what that's all about. So what we would conclude then is B matches C. Okay, so we got B matching C on that. Okay, all right. Now, this one is a quadratic, so this is kind of like x squared. What happens when you do a derivative? The power goes down 1. So if you went down to x to the first, what is the graph of x to the first? That's a line, right? Okay, and that's what happens on this one. First of all, right here, what's the value of the derivative right there again? 0, okay? Look at that. Okay, that matches. Okay, that's what we want. What kind of derivative is here, negative or positive? Negative derivatives. Negative sloping tangent line. That means the value of the derivative is going to be below the x-axis. It's negative values. Now over here, you have positive sloping tangent lines, right? Look at this. You have positive values there. So that one has to match this one. So you would conclude that C matches B. Okay? Is that sensible? Okay, I never can tell. Okay. So, go ahead.
So is when it's approaching the x line, the x value line, that's when it's a negative?
Yeah, well, it's negative when the tangent line's going down. Okay. What you have to kind of see in your mind is this. Right now, if my pen represents a tangent line, that's a negative slope, right? That's the value of the derivative. It's negative. It's below the x-axis. And then right here, it's still negative, right? But it's sort of leveling off that, the value is getting close to 0. So what's happening is, if you look at this, these are negative sloping derivatives, and eventually you get to 0, right? Then what happens? Positive, like that, see? That's the idea. Positive just means, positive derivative means the function values are above the x-axis, okay, like that. Well, I think we can conclude that the next one is got to be this one then. What do you think? Okay, B is A. And with this one, it would kind of go like this. This one actually, there's no place on this function where the derivative is 0. There's no place where the tangent line's horizontal. But what I see here is, isn't the value always negative on your tangent line? Don't you always have negative sloping tangent lines? Yep, okay, look at this. You have nothing but negative values there. They're all below the x-axis. That's the only thing that makes any sense with that one, okay? And another thing to notice on here, right there, that looks like a 45-degree angle. So if you have a 45-degree angle, the slope would be about -1. Well, that looks like that function value is about -1, Okay, that's how I reason that out and make sense of the connection between the function and derivative. All right, is there any question on that?
On that last one, on the left side of the derivative,
Mm-hmm.
that,
Are you talking about this one, D?
yeah.
Yeah.
Wouldn't that be a positive though?
No, okay, because it's all about slope of a tangent line. Okay? Remember, what you're doing over here is you're graphing the derivative. Right now, that's a negative sloping tangent line, right? And if you look at that, that's, it's some negative value. That means the value of the derivative is below the x-axis. Still negative, and then eventually it gets to that point where it's at a 45-degree angle. Then it starts getting steeper, so then it starts getting more negative. Okay, see what I mean? Okay, the slope of the tangent line on that problem is always negative. That's why all of the function values on the derivative are negative values. They're below the x-axis. Okay? Okay? All right, let's do one more thing with that, and then we will kind of start talking about continuity here a little bit then. Okay? So let's see if we could graph the derivative on this one just on the same graph. Okay? All right, so this is how I always analyze this, is like this. Okay, tell me what the value of the derivative is right there. 0, that's important. So you would just say f prime of x right there is taking on a value of 0. Okay, so that means the derivative would have a function value of 0. It would be on the x-axis like that. Okay, that's what matters. Okay. Now, I want you to look at your tangent lines here. What kind of values do you have there? Positives. You have positive sloping tangent lines all the way like that, right? So that means that your derivative is going to have positive values. Now, where is it the steepest? Over at the left or way up here at top? That's where it has the biggest. The derivative would be the largest value right here. Okay, that slope of the tangent line's big. So the way I look at this, I don't know what it is, but around here is maybe where it's around 45 degrees. What's going to happen on this is you're going to start with a big slope, and then you're just going to start kind of coming down towards the 0 like that. So that's going to be the idea. Now what happens to your tangent line over here? You have a negative value, right? So f prime of x here is negative value. So that means from there on out, it's got to be negative values like that. Now, the reason it's a line is because this is a quadratic, so it's like it's something with a second power in it. So then the derivative, we're going to learn, ends up being the exponent goes down 1, so it's a line. Okay, you'll kind of make a connection on that when we start learning derivative rules to go like that. So this right here, that would be your graph of your derivative.
No, wouldn't it always be like the 45 1 over 1 if your derivative power is the x1? It'd be like your line would be 1 over 1, right? That'd be your slope for the entire line.
Not on this one. I mean, the derivative is changing everywhere. I mean, right here is when it has the biggest value. That's where it's the steep. It's getting less steep. So like, for instance, the slope of this tangent line is a lot bigger than the slope of that tangent line, right?
Yeah. I guess
so what's happening is the derivative starts with a big value, and it gets less steep, and eventually gets to 0 because it levels off. And then the negatives just get steeper and steeper and steeper, so they get more negative.
But if you plugged x into the x to the 1 power, right?
Uh-huh.
The slope would be 1 over 1, right?
Yeah, but the thing is, we don't know. I don't know what this is not the graph of x squared. It's the graph of maybe x squared, x minus 2 squared plus something, because it's got transformations in it.
Okay.
So, yeah, if you graphed y equals x, if that was the derivative, yeah, it would be it'd always be at a 45-degree angle, right? But the point that I'm trying to make is, if you have a quadratic, the derivative is going to be x to the first power, but it may have a number in front of it, may have a y-intercept, and so forth like that. Okay? All right, let's take a look at this one. Okay, how many places on this graph is the derivative 0? 1. Okay, right there. So that's the way I always look at this. So when we graph the derivative, well, you want to put a function value of 0 right there. Okay, right here at this point in time right there, to me that looks like it's a little bigger than 45 degrees, but that's clearly a positive slope. So that means you're going to have the derivative at this value here is going to be some positive value right here. I don't know where. But what is happening to this tangent line? Is the slope getting bigger or smaller as you go through it? It's getting smaller, exactly. Okay, it's getting less steep, which means that it's going to be doing something kind of like this. I don't know, it's probably going to curve in some way kind of like that. Then what happens here is, now from here on out, what kind of derivatives do you have from there on out? Positive, and it gets steeper, doesn't it? So that means it's going to turn around and it's going to get bigger like that. So this derivative graph would do something like that. Okay, the idea of what you're trying to establish is, you know, find where the derivative is 0. That's a key. And then over here, just kind of like this. As a positive derivative, and it's steep, but it's getting less steep until it gets to 0. Then it turns around and gets steeper like that. Okay? How's that look? Okay? All right. So that's something that we're going to work on a little bit. I want you to be able to do. You want to make that connection. Okay, now we're going to look at, we've talked about continuity. Haven't talked about differentiability much yet, but we'll get into that a little bit. So this is kind of an important theorem that I want to mention a few things about, that basically says if your function's differentiable at a place, now all that means is the derivative exists. There are functions that are going to have places where you can't do a derivative. So we'd say it's non-differentiable. So this thing is a guarantee. If something's differentiable at a point, then we have to conclude that it's continuous there. Okay, remember continuous means no breaks or anything in the graph at that point. So this one would be an example, but I want to show you something on this that's backwards, so you might want to write a note down on this. So if a function is continuous, it's not necessarily true that the function's differentiable there. And you can just kind of abbreviate that right there. So see, this is a theorem. It's an if-then, okay? This is saying if you conclude that something's differentiable at some place on the graph, then you can conclude with absolute certainty that it's continuous there. But if you do it the other way, it doesn't necessarily work, okay? Now, we're going to get into this a little bit here, but I'm going to show you an idea kind of on here, and you can just make like a little rough sketch kind of like I'm doing here. I'll give you an example of this. Okay, let's say, for instance, you have a function like that, and let's say that that's like at x equals 2, okay? And let's say that I'm interested in, I find an f prime of x like that. Okay, now would everybody agree that the function's continuous there? You know, there's no break, okay? Nice and smooth, okay? The limit exists there too, doesn't it? Okay? Now, it's not going to be differentiable there, and the reason is if you tried to draw a tangent line at a sharp point, there isn't any way to do it, okay? The right idea is, when I was teaching you how to do tangent lines, I said, take a point just real close to it and connect it. So you could have a tangent line going there. But you could also connect it with a point over here. Maybe your tangent line goes like that. If you have a sharp point, you can't define what the slope is. Does that make any sense? I mean, how do you tilt it on a point? Okay, you can't make up your mind on how to make a tangent line there. So what this is although we would be continuous at x equals 2, that doesn't mean that we're differentiable there. So we're not differentiable. So what I'm trying to show you is, although this theorem works, differentiability implies continuity, it doesn't work the other way around. Okay? Does that make any sense? Okay? So if you have a derivative and it exists at a point on a graph, then you have to be continuous there. It's the only thing that makes any sense. But the backwards, it doesn't work that way. Okay, so let me go through a couple more things on this. These are good diagrams. I took this out of the book. This is what I was just trying to show you. So this would be at x equals a on this, the function would not be, it's not differentiable at x equals a. And if you look at that, what this diagram shows this real good. It's just the idea is that if you connected those two dots, that's what the tangent line looks like, right? If you connected those two dots, that's what the tangent line looks like. So the point is, when you have a sharp point, you don't know how to draw a tangent line. Does that make sense to everybody? Okay, so that's not differentiable there. We call that a cusp, okay, or a sharp point. I use the word cusp most of the time. And what happens on this is, although it's continuous there, the derivative doesn't exist there because it's a sharp point, okay? There's another situation that shows up, and it would be this thing right here, okay? This one right here, this example here, would not be differentiable at that point because you have a cusp, so that's not differentiable at a equals 0, okay, if we're looking at f of a, so it's not differentiable there. Okay, this one right here, there's one thing that happens on this next graph that's kind of interesting. There's one place where the derivative doesn't exist, okay, now just kind of do what I'm doing here. Okay, this thing's continuous everywhere, and you got a tangent line, right? Tangent line's good, it's a well-defined tangent line. What if you do the tangent line right there? What kind of line do you have? You have a vertical line, right? What do you know about the slope of a vertical line?
It's undefined.
It's undefined, okay? So it's not differentiable there because it's got a vertical tangent line. So that's another case that happens, is the derivative will not exist at that point. So this one we would also say it's not differentiable at a equals 0, and the reason is because that tangent line is vertical, and therefore the slope of a vertical line is undefined. Okay, so that's another thing that happens. So cusps is one issue, vertical tangent lines is another issue. Okay, and then places where you're not continuous would be the other issue. Okay, so what we kind of look at on this is, in this box down here, this says a function is not differentiable if one of the following conditions holds. Okay, you're not continuous, so you'd have a break, has a corner, that's a cusp. I think textbooks all do things differently. I always thought of that as a cusp. They call it a corner, and then a vertical tangent line. So those are the things that happen on a graph. You want to be able to identify where the derivative doesn't exist. Look for cusps, look for vertical tangent lines, look for places where it's discontinuous, okay? All right, so let's kind of put this together now. And what I'm going to look at on this then is, this one, what we want to do is, giving you a graph, so we're going to use the graph to do the following. So on A, we're going to find the values in this interval. First of all, where you're not continuous. Okay, now you guys have already been checked on this. Can you tell me from, and we're only going from 0 to 3, the places where it's discontinuous? That's the only place, right? It's the only break we have. So it's not, we would say it's not continuous at x equals 1. And that's because the limit does not exist there, right? Okay? All right? Now, not differentiable. Can you tell me where it's not differentiable? 1. 2. What's the deal with 2? Cusp. Good. Okay. So you're not differentiable there, and you're not differentiable there. Okay. So we would say not differentiable at x equals 1. That's because it's discontinuous. And x equals 2. That's because of the cusp, like that. All right. So that would be the idea. All right. Now, what I want to do next with this is let's draw kind of a little graph on this and see if we can get this put together here. So just draw you a little XY axis sort of here at the side. And let's see if we can draw a fairly accurate derivative on this one. This one you should be able to get pretty accurate. So let's just kind of label the X like it is, and the Y kind of like that is like this. Now our goal on this is to graph the derivative, okay? There's two places where the derivative will not exist. The two places the derivative will not exist are going to be at 1 and 2. Okay, let's just kind of reason out what we have here. Okay, right here, at this part of the graph right here, from 0 to 1, what kind of tangent line do you have here? Like right here, what does it look like the tangent line might be? Getting close to 0 maybe. But then from there, what do you have? Positive derivatives that are getting steeper, right? So when I do this, I would just kind of think, okay, we start there, and when we get there, you can kind of tell that's kind of close to a 45-degree angle. It may even be a little steeper. That's kind of hard to tell. So that's just going to kind of go up to there somewhere. I don't know exactly where, but then I'll put a bubble there because you're not differentiable there. The derivative does not exist, so you have to have a bubble there, okay? Now, if you go here, if you look at this next from 1 to 2, you can kind of tell the derivative there kind of looks like it's close to 0, right? I'm just going to assume it's 0, all right? So what we would do there is you would have to have a bubble there, and the reason is because we're not differentiable there. The derivative doesn't exist there, but then what kind of tangent lines do you have here? Negatives. So that means you're going to have to go below the x-axis, and you're just going to get steeper and steeper, so it's going to go down something like that. Then at 2, it's not differentiable, so you would have another bubble there, okay? All right? Now, the next one is real important on here. What kind of tangent lines do you have here from here on out? Positives, but they're constant, right? Okay, that's a line, so it has a constant slope. That slope to me, I don't know, what do you think? 2 over 1, 3 over 1? You're going to go with 2 over 1, that's good enough, okay? So see, I'm saying on this is you would have a bubble there, and then you would have a line going straight like that, okay? That's because that tangent line on that function always has the same slope, okay? All right, does that make sense? I don't know. It's pretty abstract, but you're looking at values of tangent lines when you graph a derivative, yes?
How come the line is straight, but it's a positive position?
Okay, because of this, okay? Look at this. I always got to stand up and show you my pen. Okay, right there, the tangent line will never change. The slope of that tangent line is always the same, isn't it? So that means the value of the derivative is always the same. We said, oh, we just estimated. That looked to me like it was about up 2 over 1. Okay, so it looked to me like the slope of that tangent line was up 2 over 1. So that means the value is always 2. The slope's always 2. Right there. So I'm saying the slope there is always 2. So that's why the derivative is like a horizontal line, because it always has a value of 2. Does that make sense? Does that make sense to everybody?
Because you're saying that it's a constant of 2.
Yes, absolutely. Right there. Anytime you have a line, if you have a straight line, the derivative is going to be constant. Okay, that has a constant slope right there. That's the reason why it's going to be a horizontal line. Okay? And that's why it's different, like at this place right here. See, this is what's different. This changes. Doesn't this tangent line change its value? Absolutely. Okay? 0 gets steeper like that. Now see, you jump back down to 0 because that's the slope of 0. Then it's negative like that. Then it jumps up to this area where it's a constant slope. That's the idea. Okay? Just makes you think. Makes you understand the connection between functions and derivatives. That's the goal. Okay? All right, I'm going to let you guys try this, work just a few minutes on this one. And I do want you to try to graph a derivative, so I'll give you a chance to try to do one of these. And then we'll basically, that's the end of this, I guess, and we'll move on to the next section. And it's hard to make your graph 100% accurate, but you want to get, pretty close to the idea. And, answer question A and B, figure out where it's not continuous, figure out where it's not differentiable. That's important. got a graph. You can compare it with your friend and see if you're getting the same kind of thing. Let's say if we got the first two things done, first of all, okay? How many places is this function discontinuous on the interval 0 to 4? 2. 1. There's only one place where it's discontinuous. Where is that? X equals 1. That's the only place you have a break. So that's the first thing you ought to make sure you have. So you're not continuous there, okay? Now, how many places is it not differentiable? 2, okay? If it's not continuous, okay, what's there, it's not going to be differentiable there. So we're going to have, that's at x equals 1. Where's the other place? X equals 2. That's the cusp. Okay, so you're not differentiable there, and you're not differentiable there. So that means when you graph your derivative, you need to make sure that you have a bubble somewhere on 1 and a bubble somewhere at 2. Okay, you have to have that. Okay, you got to make sure that you're not defined there. Now, the way I've done this is I just kind of chop this up into key things. I always try to find where the derivative is 0. So right here, even though the derivative doesn't exist there, well, you can tell the derivative is close to 0, right? Okay, so I would think at 1, when x is equal to 1, we know we're not differentiable there, but we know that derivative is around 0. So you'd have to have a bubble there, okay, like that. Okay, now look to the left of that. Right here, what kind of slopes of tangent lines do you have right here? They're all positive, right? You have positive sloping tangent lines right there. And it's the biggest value right here. That's when the tangent line's the biggest. If you look at the slope of the tangent line, that's around 1, maybe a little bigger than 1. You don't know, okay? So what I would do on that is just estimate that slope right there is around 1. Okay, the derivative does exist there. And then it just gets smaller. So it's going to go through and kind of do something like that, say. Okay, does that make sense? Okay, all right. Now, what kind of derivative do you have from 1 to 2? Negative. That's what you care about. Okay, and when you get down to that point, even though the derivative doesn't exist there, it looks kind of like that maybe that slope's -1. It's around 45 degrees. Close. All right. So that means what's happening here is your derivative, you're going to go down to there where the derivative's not defined, but you have negative values, but it's getting steeper. Right here, it's just barely negative. Then it does something kind of like that. That's going to be probably a straight line like that. Okay, is that logical? Okay. Now, between 2 and 3, what happens to the derivative? It goes back to what? Positive. And it looks to me like right about there, it's the value of the derivative at that cusp is about 1. So if you go there, you would probably go back up to about 1 like that. And then when you get to 3, the value of that derivative is 0. But does the derivative exist at 3? Yeah, it's differentiable there, right? So you got to have a solid dot there, okay? And then what's going to happen is between 3 and 4, you have a negative derivative. So you're going to have something kind of like this. You got positive derivatives from 2 to 3. Then you got negative derivatives from 3 to 4. And you close off with like that. The only place that you should have bubbles is the 2 places where it's not differentiable. So you'd have ones there and there like that. Okay? Is that logical? I don't know. Yeah.
I just have a question. Why did we go down to -1? I just have no idea.
Which place?
On both.
I see basically 2 places where the derivative's about -1. One place would be there. That's a negative sloping tangent line at approximately a 45 degree.
Oh.
So at 2, I went down to -1, but I put a bubble because it's not differentiable. The other place where the slope's around -1 is at 4. Okay, so I went down there and I put a dot there because you are differentiable there. So there's only 2 places where you're not differentiable, and that's at the place where it's discontinuous and at the cusp. Does that make sense?
Yep.
Okay, any other questions about that?
-1, alright, 2, -1, how come, since the slope is 1, we didn't just go up 1 to 0? How come we went up to?
Okay, well, see what's happening right at 2. Okay, when you're barely to the left of 2, your derivative is negative. You're barely to the left of it. Okay, but then what happens is on the other side of the cusp, it jumps up to positive. So it kind of like does this. It jumps. You have a derivative there of around -1, but then when you get barely past 2, it jumps up to 1. And then what happens is the slope gets smaller, and it goes to 0, then the slope gets negative, say like that.
So if I was to look at this, the derivative graph, or the derivative function, I should automatically see that where 2 is, that's where the cusp is.
Yes.
And I could just
Well,
analyze from there.
you tell that we're not differentiable there. And the cusp, it's just a place where the slope jumped just immediately. Like from -1 to 1. The slope changed from negative to positive. So that you got that big discontinuity in the graph of the derivative, okay? All right, any other questions? Yeah.
Before we get on to the next section, I was wondering what's the cost? Is there a specific amount of point that you need to become a cusp? Or is it just even?
It's no, what happens, not necessarily, it's just, you would have a big break in a definite jump between the slope on the left side and the slope on the right side. A good example of a cusp is an absolute value function of some sort. And what will happen on that is you have a jump immediately from one value to another.
Right, so if we had a cusp in a line that was technically 1 degree of change, that would still have no...
Yes, as long as there's a gap, okay? As long as there's a gap and you're not changing in tiny increments. If you got a gap, then you got a cusp. Okay, it changes from one to another pretty